Good morning. Welcome to physics today. I am not there, obviously. Today is Wednesday, the 22nd. Let me change that because I have that power. Haha, it is the 22nd. Wednesday, I'm not there. You have a substitute. If you're in period 1, Mr. Gussick should be with you. If you're period 2, Miss Evans should be with you. And I will be back on Friday. Still in the hospital, as you can see. No baby yet, but it's exciting times. So it is late. It is like almost 10:30 at night. So I'm trying to get some sleep, but I wanted to make sure that I get this information to you so that you will have success in the next few days. And we do have a lab today, so want to make sure you're set up for success for that. Warm-up today. So I'm going to read the warm-up, and then whoever's playing this video, please pause it once I'm done reading the warm-up. That way you can work with the students on getting this warm-up done. Mr. Ekman, he's in a tug-of-war with 3 students. He pulls with a force of 500 newtons, while the other students are pulling with a force of 200 each. Your job for this warm-up is to draw a diagram that depicts the above-mentioned forces. Tell me the net force of the situation. What direction are they going to accelerate in? And if I take the entire mass of Mr. Ekman and the 3 students together as 250 kilograms, what is the acceleration of the group? So you should be using Newton's second law, which I know you guys should have learned yesterday from the videos that you watched, and figure out the acceleration of that group. Please pause the video now. I'll make a good face like this, and you can pause the video and work on the warm-up. I'm going to assume you paused the video because I'm going to keep talking now. How would I do this problem? So here's my little canvas here that I'm going to draw on. I don't have a fancy iPad, so my drawing's not going to be very good. But what I'm going to do is I'm going to insert a shape. I'm just going to insert a box right there. So this is my box. I would just draw the outline of a box if I was doing this on the whiteboard. And this is going to represent my system. That is my box. I'm also going to insert an arrow right there. This is my arrow, my first arrow. I will make a duplicate of that arrow and just flip it around. Super fancy schmancy. I'm going to draw it like that. Now you notice, I understand it's not perfect, but this arrow coming off the box is shorter than this one. So this one's longer. I would say, let me insert a text box. I would call this force students. Students being a subscript. I can't really do that on the computer, but for students. And then I would have right here, I would say force Ekman. That's how I'm going to define them. So I have force students and force Ekman on my little canvas. That is my diagram of the situation. If I were to add up all those forces, I would say force students, that's force Ekman. Let me shorten that. Force students, I know force students is 600 newtons total. So I'm going to say equal to 600 newtons total. And force Ekman is going to be equal to 500 newtons total. When you are calculating net force, I'm going to take the force from one side and I'm going to subtract the force from the other side. And that's going to give me that net force. So the net force I have in this case is 600, which would be on this side. 600 minus 500, which gives me 100 Newton force. So let me copy this arrow. I'll shorten it a bit. I'm going to say there is 100 Newton force, or, nope, that's not what I wanted to do. I want to copy this. I would call this my force net equals 100 newtons. So that means that if I add up and subtract the forces that are on this system, there's 100 Newton force that way. I think that way. There's 100 Newton force in the direction of the students. That is what you are seeing. That means that they're accelerating in that direction. Acceleration comes from unbalanced forces on a system. If Mr. Ekman and the students were pulling with the same amount of force, there wouldn't be any movement. But since the students are pulling harder, there is a much stronger movement. Hopefully that makes sense. I know I'm rambling. It is late at night, but we're going to move forward. The next part of that question, if we look back at our question, if the combined mass of the group is 250 kilograms, what is the acceleration of the group? So what I need to do, and hopefully you all can see this, is I'm going to use my equation, force equals mass times acceleration. What I know is my net force. So I'm going to think about my givens. My force equals 100 newtons. My mass equals 250 kilograms. And my acceleration equals question mark. I'm setting it up just like the guess method. So then I just have to plug in my values and solve for acceleration, just like I would if I was doing a kinematics equation. All of you have a calculator, so if I plug that in, I'm getting 100 equals 250A. Solve for A, I divide 250 on both sides. I'll get 100 divided by 250. If I put that into a calculator, I don't know off the top of my head. Actually, I'm going to pull my calculator out because I'm going to be a good student today. 100 divided by 250, and I get 0.4 meters per second squared. That is my acceleration of this system. Hopefully you all had a chance to do that on your own. Sorry that my explanation is so frantic, doing it from the hospital on a computer without the whiteboard in front of me, but hopefully this was helpful hearing it from me. The lab. You should have the lab materials with you. You're going to be using a track just like we use for our acceleration lab. You're going to be using those same carts, but what you're adding to that is you're adding a pulley system, which will be on the end of the cart, and the substitute or Mr. Gussick or Miss Evans will show you what that looks like. And there's going to be a hanging mass, a little hook thing. This lab's in 2 parts. I expect this to take you 2 days, both today and tomorrow, to finish and turn in. So I'll make the submission link for tomorrow. But the first part looks like this. That's our little system. I have our cart. It's moving. There's a hanging mass, and there's our little pulley system. The questions that our first part is trying to answer is what force is causing the cart to move, what data and equation will you use to calculate the acceleration, and what is staying constant, and what are you changing from trial to trial. The way you're going to do part 1, just so there's no confusion, and write this down. The way you're doing part 1 is you're going to start with a mass on the cart, some large mass. You can use those bar masses if those are there on the cart with you. And you're going to add bar masses or some mass or weight to the cart. You're then going to do the time for that, proper science. We're going to take 3 trials each time, take the average. You're not going to have any weight on that hanging mass. That is not going to change. That little hook thing, it weighs 5 grams. You're not going to change it. It's going to stay the same for part 1. What you're going to do is you take the cart, you're going to have a mass on it. You'll take how long it takes for that to move down. Then you're going to remove one of the masses and continue until you have your 5 data sets. So there should be 5 different masses for your cart. You're changing it each time, starting from a high number going to a low number. And you're never changing the mass on the hanging mass. This whole system, I know I said all that, but this whole system should be hanging off the table. So your teachers can help you. Part 2 is a little different. You're going to be using the round masses specifically. You're going to start with masses on the cart, just like you did before, some mass, and then you're going to take the mass off the cart and put it onto the hanging mass. And you're going to do that each time. So that's part 2. If you have any questions, please email me. Talk to your teachers. They'll know. They've at least Mr. Gussick and Miss Evans have seen this before, so please rely on them. Hopefully this has been helpful. Hopefully I didn't just waste your time. Have a great day. It's great to see you, and I will see you on Friday.